Okay, in this video we want to look at some applications and some uses of the scalar product. Now, to motivate this, I want to show you that this scalar product, this idea is not just some abstract mathematical thing. It's something that has real-world applications. So, for example, one of the real-world applications of the scalar product is calculating something called the work. And so imagine I have a box here, and I want to pull this box and slide it across the floor. And so I attach a rope, and I'm pulling up at some angle with a force. And this box slides across the floor. Now, the work is defined in terms of the scalar product. And we're going to actually define work much more carefully later on, but just to give you the idea. What this means is that if I have my force vector F, which is at an angle to my motion, that force, not all of that force is going into making it slide to the right. And I could actually break my force vector into components. I could break it into a component that is parallel to the motion, like that, and a component that is perpendicular to the motion. And so what that practically means is that part of the force is lifting the box up, and part of it is making it slide across the floor. And so if I had my box, and I drew my box, and I had the force going directly in line with the way that the box is sliding, 100% of that force would be going into making the box move to the right. But in this situation where the force is at an angle, the entire force is not going to make the box go to the right. Only part of the force, specifically the part of the force that's parallel to the motion, that's the only part of the force that's making the box move to the right. And so that would be the part of the force that is involved in doing the work. And so really this work, if I wanted to write it out, would be the magnitude of the force times the magnitude of the displacement, how far it slid, and then times the cosine of the angle theta. And that cosine of the angle theta picks out the part that's parallel to the motion. And we can see that's just the scalar product. And so work in general is going to be a scalar product. That's just a physical example of something where this math can be applied to. Now, as we'll see as we go through our study of physics, that the scalar product has lots of uses. It's used to calculate energy and power. It's used in the study of electricity to determine the forces acting on distributions of electrical charges. It's used in the study of the motion of fluids. It's used to calculate the flux of a vector field. That's something you're going to learn about in calculus and in physics too. It's very useful in the study of electricity and magnetism. It shows up everywhere in physics. And so this is something very foundational. We're building this mathematical foundation so that we can understand how to apply these tools that are going to be very useful for understanding different aspects of nature. So let's just look at some examples. And so here's the first example. I've got a vector A, and I've written it in the alternative notation using I hat, j hat, and k hat, just because you need to see that notation too. I want you to be able to use both the x hat and the I hat versions. So remember, I hat goes with the x, j hat goes with the y, k hat goes with the z. And so this is the x component is 6, the y component of A is 3, or actually negative 3, and the z component of A is positive 3. And then B has components 3, 2, and there's an understood 1 in front of that k. Now, remember what the formula for taking the vector product is. We said that A dot B is equal to AX BX plus AY BY plus AZBZ. That's what the formula tells us, so we're just applying that. What is AX? AX is simply 6. What is BX? That's the component of B. The X component of B, that's 3. And so that first term, AX BX, I just plug in 6 times 3. For AY BY, I plug in negative 3 times 2, negative 3, 2. And this 3, 1, that would be AZ, BZ for that third term. And so now I just have some arithmetic to do. I multiply, I get 18 minus 6, 3. I add all these together, and so that tells me that my scalar product, A dot B, is equal to 15. And again, that's not a vector, it's a scalar, hence scalar product, just a number. No x hats, no y hats, no z hats, no I hats, j hats, or k hats, no vectors of any kind allowed when you look at the answer for the scalar product, because it must be a scalar. Okay, so here I have two vectors, A written like this with 4x hat minus y hat plus 7z hat, and I have my B vector, which is 2y hat minus 3x hat plus bzz hat. Now, what does this mean, bzz hat? That means that this component, the z component of vector B, is an unknown. So I haven't plugged in a number yet because I don't know what that number is. And the problem is to find the value of bz such that these two vectors, A and B, are perpendicular to one another. So a couple of notes before we do this. First is our key insight, which we've talked about before. Perpendicular vectors have a scalar product equal to 0. So our strategy is going to be to set these two vectors, set the scalar product of these two vectors to 0, and then multiply everything out and solve for our unknown. So here's our problem. I want to look at these two vectors because I did something a little sneaky here. I said my A vector is 4x hat minus y hat plus 3z hat, but my B vector was written 2y hat minus 3x hat. Do you see how sneaky that is? The normal order is reversed here. And so you want to pay attention to this because when you're multiplying out the numbers to form the scalar product, you don't go first to first necessarily, you go x hat to x hat, you go y hat to y hat, z hat to z hat. And so I would actually, if I had a problem like this, I'd probably want to write everything out and put it in the correct order. So again, I have my problem written out up here. I'm looking at these vectors. I've rewritten them now, so I've got my A vector is now what I had before, but my V vector, I've changed the order, so I've got this is minus 3x hat plus 2y hat plus bz hat, bz, z hat. And so I'm simply going to multiply the x parts together, the y parts together, and the z parts together. So let me show you how we would group those together. So the x parts are going to be grouped together. So I'm going to multiply 4 and negative 3 together. Now, when I look at this next term, the minus y, remember that there's a negative 1. There's a 1 implied there. And so I want to group my negative 1 with my 2, and I'll multiply those together. And then I'm going to multiply my 7 and my bz together. And all of these things get, once you multiply them, you add them up. And so I'm going to add those up together. And so that's what I have here. So I've got 4 times negative 3, and then I've got minus 1 times 2, and 7 times bz. And all those groupings are added up together. And so when I simplify this, I end up with 7bz minus 14 equals to 0. And I think everybody would agree that that's easily solved to give bz equals to 2. So what does that mean? I can plug in any value I want for bz and I will just have two vectors. But if I plug in 2, that means that A and B would be perpendicular because that's the value of bz that makes their scalar product equal to 0. Now here is a very common use of the scalar product. If I have two vectors that have written out here, I've got A vector, 5x hat minus y hat plus 3z hat. I've got B vector, 2x hat minus 3y hat plus 4z hat. I want to find the angle between them. So this is the problem. I've got two vectors written in component form, and I want to determine the angle between them. So if I look at the fundamental definition of the scalar product, the geometrical definition, I know that A dot B equals A magnitude B magnitude times the cosine of the angle between them. That tells me that that might be a key to finding the angle because this is a term involving the scalar product and the angle. So what I'm going to want to do is solve for theta. And so if I divide both sides by the magnitude of A and the magnitude of B, I can isolate the cosine of theta and get it by itself. And so I can say that the cosine of theta is going to be A dot B divided by the magnitude of A and the magnitude of B. And keep in mind, the magnitude of A and the magnitude of B, those are just scalars. They're numbers. They're the lengths of the vectors. So they're just regular numbers too. And so in order to do this, I need to calculate what A dot B is, and I need to calculate what A magnitude is and B magnitude. So calculating A dot B is easy. I just take the x parts and multiply them together, 5 times 2, -1 and -3. And I just realized I made a mistake because that should be -3 in there. And that would make this +3. And so that answer is actually wrong. But you can see how what we're doing. So again, I've got the 5 times the 2, and so there's 5 times 2. I've got the -1 times the -3, so there's -1 times -3. And then I've got the +3 and the +4 multiplied together. And so that's going to be equal to 5 times 2 is 10 plus 3 plus 12. And that's going to be 25. And that's going to be my answer for A dot B. And of course, that's going to throw up the rest of my calculations, so I feel kind of stupid, but I'm not going to bother going back and fixing it. I'm just going to proceed and correct it as we go, because this is part of life. You make mistakes. And, you know, it's kind of good in a way that I showed you guys that even I make mistakes. I've been doing this forever, and even I screw up sometimes. So, you know, if you guys get frustrated by mistakes that you're making, don't. You know, it happens because you're a human being. And we'll just press on and continue, because what's important is that you get the idea how to actually do this. Okay, so again, I've got my A dot B should be 25, not 19. And so I want to form this for cosine of theta. And I've got my A dot B. I know that's 25. I now need to find A magnitude and B magnitude. And so A magnitude is simply, we're going to use the three-dimensional Pythagorean theorem, and we'll plug in the x, y, and z components. We'll do the same thing for B magnitude, and we get 5.92 and 5.39. Now I'm going to correct this again. This is not 19. Of course, that's going to be 25. And so that means that if I calculate the cosine of theta, and that turns out to be equal to 0.7834 or 35 actually, with rounding. And if you take the arc cosine of that, you get 38.4, or yes, 0.4 degrees. So that would be 38.4 degrees. And so that tells me the angle between those two vectors, A and B. Now, in this slide, I've listed a few properties of the scalar product that are good to know. And so just wanted to quickly go over some of these. Of course, the first one is the commutativity property that we've talked about. Basically, it says the order that you do the scalar product doesn't matter. This is showing how the scalar product distributes. So if I've got A dotted into some vector sum B plus C, you just distribute it like you normally would. That would be A dot B plus A dot C. If I have a scalar multiplied by one of the vectors, it can just come out front if you do, so you would distribute this as normal. And of course, we've already kind of seen this already, but if I have a scalar times a vector dotted into another scalar times a vector, you can just pull the scalars out front and then do the scalar product as normal. Two vectors, A and B, are perpendicular. This symbol IFF, that means if and only if. So that's a mathematical notation. So two vectors are perpendicular if and only if their scalar product is 0. If I have a vector dotted in itself, that's A magnitude times the cosine of the angle between them, which would be 0. And so that's basically the magnitude squared. And remember, the magnitude of a vector is just a scalar. And so when you actually take a dot product of a vector with itself, you can write that as a squared. And a lot of times, probably not in our class so much, but in more advanced things, you'll see sometimes that if you have a squared from something that comes from a vector, you can simply go backwards and write that as a dot a. And the last thing I want to look at is the product rule, because the product rule applies to vectors as well as regular numbers. So if I have a derivative of a dot b, I would take a times the derivative of b plus the derivative of a times b. Of course, by times I mean scalar product. So that's just like doing the product rule from calculus. That applies with vectors as well. So anyway, that's probably a good stopping point for the scalar product, and we'll look at the vector product in the next series of videos.